Morning, everybody. Last time we had stopped off in the middle of this problem. What we're trying to do is calculate the transient response for a Miller inverting integrator op amp with an input signal that looks like this. This 1 millisecond pulse with a height of 1 volt. And I don't have drawn here the full amplifier. This was the simplified version of the circuit that we derived by applying the ideal assumptions, which include the virtual short and the assumption that there's no bias current flowing into either one of the inputs. So we're not going to go through the whole beginning again because it's relatively long. What we are going to do is just very quickly breeze through the beginning steps and then jump back into where we hadn't completed stuff. Now, one thing I did add here that I think is important and we didn't necessarily talk about in the beginning was what are the basic steps in even doing this process? Because we sort of started without laying out a roadmap of how we wanted to finish. So how we do this is essentially this is the most important step. In order to determine what the transient response is, we need to take a convolution, which I'm sure is probably a dirty word to many of you from remembering how complex it is to do those in the time domain, to perform a convolution of the input signal and the transfer function. Okay. Now we could do that in the time domain. The math gets relatively sticky. But in the Laplace domain, it's a lot easier because convolution is simply just multiplying two signals together. So with the understanding that we have to do this, and we want to do it in the Laplace domain, what we'll do is first derive or convert our transfer function to the Laplace domain, and then take our input and also convert it to the Laplace domain, perform the convolution as a product, and then last, we'll take our output and go back to the time domain. Now, we completed this. We got to the very beginning of this, and we still have the rest of this to do. So very quickly, going through what we did. Okay. We used KCL to describe our circuit's behavior, and then we converted that, or we made a first-order differential equation out of that, right, which is shown under step 2. We then defined what were the Laplace transforms from the transform table that made sense to use. The most important ones were the most basic, which is what is the Laplace transform of any function in time, and then what's the Laplace transform of a derivative of that function in time. Again, we're going to keep using the principles of superposition. This is a linear operator, which means that we can apply additivity as well as homogeneity. We can pull out constant coefficients. We can also take the Laplace transform of additive elements separately. And so when we took our first order differential equation from the time domain down to the Laplace domain, we ended up with this. We did a little bit of algebra, combining some terms together and simplifying, and then we ended up with a transfer function that looked like this right here. We removed the fraction from the denominator, and we ended up with this. One thing I actually didn't point out was that we already had this answer. Actually, if you go to the lecture notes, the slide that presents the integrating op amp with the parallel resistance, this was the frequency response. So anyway, next step. So now we're moving on to stage 2 of the problem, which has to do with the input, and this is where we left off. So we need to define the pulse input in the Laplace domain. And what we saw was, when we looked back at our Laplace table, there was no entry for that pulse specifically, okay, which means we need to make one, or we need to cobble one together with different components. So the way that we did that was using the Heaviside function, or what we call the unit step function. And so we do know how to take the Laplace transform of a unit step. But first, before we do that, we need to create our pulse from those unit step functions. So here in the red, again, is the basic unit step function, where the height is simply multiplied by alpha. Then in the blue, what we did was we flipped it upside down, so the height is negative alpha. We also shifted it to the right by time of beta seconds. And then when we add the red and the blue together, we get the purple, which is a pulse that looks as we expect it to. So our input function in the time domain will be alpha u of t minus alpha u of t minus beta, where alpha is 1 and beta is 1 millisecond. However, for the purposes of this problem, we're just going to go ahead and leave it as alpha and beta. So what that does is it allows us to find a little bit more of a generalized solution for any pulse of any height of any length. Okay? So we'll get a closed form solution that won't work for any input, but it'll work for any pulse. So our height is alpha and our width is beta. So that's where we stopped. Now, converting this to the Laplace domain, so there's 3 Laplace transforms that we need to be familiar with. One is going to be the Laplace transform of a unit step function, which is equal to 1 over s. Next, how do we apply the time shift property of Laplace transforms? We know that the Laplace transform of f of t is equal to f of s. What about the Laplace transform of f of t shifted by beta? Okay, moving it right or left. Is that going to be f of s minus beta? I mean, as you can see, it doesn't work like that. F of t minus beta becomes e to the negative beta s f of s. So what happens is the time shift does not become a shift in the Laplace domain. It becomes this coefficient, this multiplier, e to the negative beta s, where the shift is denoted by the beta value. And so, if we were to take the Laplace transform of the second element here, Laplace transform of negative alpha u of t minus beta, we can pull out the negative alpha, that's going to be outside. We can take the Laplace transform of u of t, which is 1 of s, and then we have to make sure to include this time shift coefficient, which is going to be e to the negative beta s. So our answer, when we take the Laplace domain or convert this to the Laplace domain, is going to be alpha 1 over s minus alpha e to the negative beta s 1 over s, which is shown right here. So that was a lot of repeating the words s and alpha over and over again, but hopefully this makes sense. And if you need a little bit of catch-up, right, remember, this is all going to be in the lecture videos. Actually, the lecture video from last time is already posted, so you can go back and take a look at this, the beginning of this problem, and then, unfortunately, it spans 2 videos. You have to look at one and the other, but the end of last video and then the beginning of this video right now addresses the end. Okay, so let's continue on. So we've gotten through 2 steps. If we go back up here in our overview, so we're done with that. Now, perform the convolution in the Laplace domain, which very nicely is just going to be multiplying the 2 together. Now, we didn't explicitly give it that name, but right, I would call this here, that's the transfer function for our system that we're looking at. And then we've already said that this is our VI of s. So we have VI of s, and we have t of s right here. Okay, so let me see if I can copy this. That way I make sure not to copy anything wrong because there's a lot of different variables and stuff. Okay, so that's the starting point. So this is a huge chunk of the, so the convolution's done. That step's actually really easy because we just multiply. The hard part is this fourth step. So go back to the time domain. So we have our answer in the Laplace domain. That's our output. Going back to the time domain, does anybody remember what the strategy was for that? So you have this Laplace table, correct? And essentially, unless we're going to use the definition of a Laplace transform, which we're kind of assuming that we're not going to use, okay? Because again, that would be trying to apply the definition of Laplace transform in reverse to this would lead to some very, very messy math. So we, for better or for worse, want to use the Laplace transform table. The problem is there's only certain entries in the Laplace transform table, right? There's not one that fits this. So our goal, if you remember back to Ch02, is to try to break this down into pieces that look like elements from the Laplace transform table. And we don't need the entire thing to fit that form. We just need the individual added components to fit the form. So let's say if we get one added element that fits this one, okay, good. We'll use that inverse Laplace transform. The second one fits another. We just need to work out so we can put everything into a bin and just apply the inverse Laplace transform. It's not a really easy process. The algebra can be a little bit funny, and also it requires some intuition, because what you have to do is you have to look at, the form that you have, and then you have to look at what forms are in the Laplace table and say, okay, what is my strategy? What forms am I going to be striving to achieve? So let's start off by doing that to give us a little bit of an idea of what might make sense. So I have a Laplace table loaded. And looking at our form the way we have it right now, we're at this top point here. So let me see if I can zoom this in. So we're currently up here. So it seems like our best strategy is going to be to try to get this into a form of something over S and potentially something over S minus alpha, right? Because, we can break, and again, this is a little bit of intuition again, but we can break these pieces up into 1 over S times alpha times 1 over S times beta, right? We know that we can find the roots of the denominator and then split it up in that manner. I'm not going to go into too much detail right now because we're going to do all that. But all we really need is just a desired endpoint. We don't have to know exactly what it's going to look like at the end. So if we look at the table, we can see more or less we're going to be aiming for this entry as well as this entry right here. I mean, we don't have any cosines or sines. We don't have any repeated roots, at least not that we know of. So, I mean, really all it's doing is giving us a starting point. So we know that's sort of what we're striving for. And the good news is that you'll see there's several strategies that we're going to use over and over again. One of the main ones is going to be the partial fraction expansion. Does everybody remember what the partial fraction expansion is? So, picking up where I just left off a second ago before we had the technical issue, we need to make this fit elements from the Laplace table using partial fraction expansion. And this is going to be a common strategy we use over and over again. And we've kind of already seen what elements that's going to lead us to in the actual table. So let's talk about partial fraction expansion just for a second. There's two different ways to do it. There's a shortcut way and there's the formal way. I'm just going to talk about the shortcut of doing it. So let's say you have something that looks like this. So we have 1 over s minus alpha times s minus beta. Okay, and that is going to be equal to something called gamma over s minus alpha plus delta over s minus beta. Okay, so that's the form. How do we, the unknown is what is gamma and what is delta. What are the numerators of the two elements of the partial fraction expansion? And so what they are, gamma is going to be equal to, so first thing I'm going to do is I'm going to write out the original equation. Then what I'm going to say is, well, what is the root or the 0 of this term? What is the 0 of s minus alpha? Alpha, right? So what I'm going to do is I'm going to ignore that term. And then plug in alpha down here for the s. And what that leaves us with is that. So it's almost, one way of thinking about it is you almost like you cover it up with your hand, so you get rid of that part, and then you plug in the 0 that you're looking for, or the 0 associated with the coefficient you're looking for in here. So 1 over alpha minus beta, and that becomes what you're going to put right there. Okay, next, let's try the one for delta. So delta, we can just do it. We know that the 0 is going to be beta, and we're going to plug that now into this term. Whoops. We're going to plug that into this term right here. So what that'll leave us with is 1 over beta minus alpha. All right. So now there's an extended way of doing the partial fraction expansion. There are a couple caveats here with doing partial fraction expansion. If you have repeated roots, or complex roots, then sometimes you can't use the shortcut. But honestly, for the example that we're currently working with, the shortcut works just fine. All right, so next step, step number 10. And I'm just going to say, because there's a whole bunch of steps in here, I'm going to say use partial fraction expansion plus just good old algebra to put VOS into the necessary form. That's really the best way to describe it, because it is an open-ended process. As we move forward, we'll start to see, okay, well, I need to separate out this term. This one is looking more like this entry from the Laplace table, etc. Okay, so we start off with V out of S is equal to negative alpha RF R1 RF CF. And I guess right off the bat, well, I'm going to leave the RF there for a second. I think I'm going to use it later. Although, ideally, right, that goes away. So I'm going to pull out as many of the coefficients as possible times sorry, I'm looking at the wrong thing here. Okay, so if we look, trying to get both of them in one screen. So if we look at what we have just to verify the multiplication, right, we will have alpha times this, 1 over S times this. That'll give us negative alpha RF over R1, S plus S squared RFCF. So that's the combination of those two together. The next piece which there's a minus missing. No, the minuses cancel out. Right? So you have, so these minuses will cancel out, meaning the second term will be positive. So you'll have the same thing, alpha 1 over S times this. So that's the reason why you see this piece and this piece are exactly the same. But the second added component is multiplied by e to the negative beta s. So this is the transfer function with the two pieces separated out. Again, our goal is to divide and conquer. At least now we can analyze this separately from this one. Now we'll see that we don't have a form that fits this right here. Actually, we don't have to worry about this. Does anyone know why we don't have to worry about this? Well, it's not a constant. It has an s in it. But we know how to deal with this in the inverse Laplace transform. It's going to be a time shift. Okay? So this we don't have to get rid of. This will, essentially, these are going to give us the same function. This is going to be function f, whatever it is, and this is going to be that same function shifted by a beta. So it's almost like, even though we have two parts, it's almost like we're just trying to solve the same thing twice. Essentially, what we need to do is we need to get this into a form that fits the Laplace table. Like I've said a million times, All right, so we're going to use partial fraction expansion right there. All right, and what I'm going to do is I'm going to address the pieces separately. So, because it's really, we're going to be doing the same partial fraction expansion 2 times. So what I'm going to do is I'm going to take this piece right here. All right, and we're going to call this, we'll just give it a name, G of S. Okay? And we're going to apply the partial fraction expansion to G of S, and then we can plug it back in, because really, right, G of S is also right here as well. Okay, so let's do the partial fraction expansion on G of S. So first things first, let's pull out all of the, well, first things first, let's split it up into the 2 roots of the denominator. So we know this will be negative, the numerator stays unchanged. And actually it'll, well, no, we know what it is. It's going to be S times 1 plus S R F C F, right? However, we're more used to seeing the roots in the form, right? We want the form S minus something. So in order to do that, what we can do is multiply the numerator and the denominator by 1 over RFCF. Okay, and what will happen is then we'll get something which is more like the traditional form we are used to seeing, which will give us negative alpha RF R1 divided by RF CF over, and now this will become S times S plus 1 over RFCF. Right? Okay.
Professor?
Yep.
Was there something you did to, I'm not sure if it's a mistake, but RF times R1 being the numerator?
Mm-hmm.
I think that should be, it should be divided by R1.
Oh, yeah, you're right. Yeah, that was a mistake. Thank you. Yeah. All right. So now we know what the zeros are. So the zeros will equal, obviously, 0 over here, right? Because when we plug in the 0. And then the 0 over here will be equal to negative 1 over RF CF. Okay. So now we So the takeaway from what we did up above is that our desired form is going to look like this. We don't know what is going to be in the numerator just yet, but that's the partial fraction expansion. Okay, so now we have g of s, again, is equal to, so I'm going to go ahead and pull out all the coefficients that are right here. So that gives us negative alpha RF over R1, RF, CF. And then our second piece now will be equal to and I just need to give it an unknown name. So what's the symbol I haven't used yet? I'll call it uppercase A over S plus uppercase B over S plus 1 over R F C F. Okay. All right, so maybe it would have been easier to split this up into multiple steps, but right now we're sort of taking it from this approach. So, so what is our A? And so I'd like for you guys to tell me that. So we're trying to apply a partial fraction. We've already pulled out the coefficient. So it's 1 over S times S plus RFCF. So our first 0 is S. So we're going to cover up this part. And then now we're going to plug in the 0, which means we're going to plug in the 0 right there. So it'll give us 1 over RFCF. Right? That's what happens when we apply our shortcut. Does that make sense? Yes? No? Again, we've taken this part away, so there's just a 1 left up here. Cover up the 0 we're working with, or the root that we're working with. We know the 0 of it is actually 0. So then we plug in a 0 right here. So we end up with 1 over 0 plus 1 over RFCF, which is the same as 1 over RFCF, which is RFCF. Okay. So now we get our B. So for our B, we go back up here. And remember, just for a second, we'll put a 1 up there because we removed all that stuff out anyway. So our 0 here is negative 1 over RFCF. So we're going to cover up this piece. Now we're going to plug in the 0, which is negative 1 over RFCF, which will give us 1 over a negative 1 over RFCF, which is equal to negative RFCF. It's a careful balance here. I'm trying to give detail without going super into detail. So hopefully it's enough that those who know it well will get something out of it. Those who don't know it well, will give them at least a starting point to perhaps dig a little bit deeper. Because what we will end up with is 1 over Okay. And then so in the end, what we end up with after the partial, so now our partial fraction expansion is complete. All right, and so what we end up with is g of s is equal to, we have to not forget about our little beginning part, so negative alpha rf over okay, and then now what we have is and this is good because you can see now we have added components that all fit with the forms that we see in the Laplace table, right? We have a form in the Laplace table that fits 1 over s, and we also have a form or an element in the Laplace table that fits 1 over s plus something. All right. So we've done a lot in this step. Step 11. So we are going to essentially clean up the math by inserting the results of the partial fraction expansion shown in what we were calling g of s into our VO of s. So we have, if you go all the way back up here, we have this as our output. Embedded within it is the g of s, 2 times actually. Then, now we have this expanded form of g of s, and so we just have to plug it in 2 times and then split it up. So it's a lot, but at least it's in the right form, actually. So that's good. So why don't I copy this, and then we'll plug in what we need. Okay, so that's everything together in one place. You can see our original VO of s, and you can see we have our new g of s, and we got to plug that in there, and we also got to plug it in right here. And so the equation's going to get long. I'm not doubting that part of it, but we do have it in the form that we need it Okay, so let's go ahead and expand this. Now the nice part is actually we can pull a lot of stuff out and make longer coefficients, which will shorten the fraction parts. So the first coefficient, or the coefficient for the whole thing, is going to be negative alpha RF over R1 RF CF. Okay, so that takes care of all of these. Then what we can do is from each one of those pull out another RF CF. So that'll make this RF squared CF. And I know that's a messy coefficient. We need to eliminate some terms, but I'm going to leave it the way it is just for right now. And so after we do that, then what we'll be left with is all ones in the numerators. So we'll have 1 over S plus a negative 1, because remember this is negative 1 RFCF. Negative 1 over S plus, and this is going to be 1 over RFCF. Now we have the exact same thing repeated, right? Because we have it here, and then now we have it here again. So again, we'll have 1 over S plus negative 1 S plus 1 over RFCF. The only difference is we can't forget that this term is multiplied by e to the negative beta s. And the one other thing we have to take into account is actually this was a negative and this was a positive, so the second term should be minus. All right. Okay, so now, we're almost done actually. So what inverse Laplace transforms are we going to use? I think we listed those out somewhere up above. Well, essentially, there's two different forms that we have. We have to deal with inverse Laplace transform of 1 over s, which is going to be equal to u of t, right? Then we also have to deal with inverse Laplace transform of 1 over s plus, well, I'll just go ahead and, well, I'll use an unknown. So I've used so many letters, I don't know what letters have been unused. We haven't used mu yet. Okay, so mu. And that gives us, if I look at the Laplace table, it gives us e to the negative mu t. Normally they use an a there, but we used an a somewhere, so I don't want to reuse it again. Okay, so that will address this term. That'll address this term. Now the remaining terms will be this combined with that, right? It'll be 1 over s times e to the negative bs, but that's easy because that's just the time shift. So now what's Laplace, inverse Laplace transform of 1 over s e to the negative b, or beta s? That's equal to u to the t minus beta. All right? And technically, actually, the definition of the Laplace transform, everything is everything has a u of t that is multiplied by. That's just the definition. And so then the last one that we don't know is what is going to be the inverse Laplace transform of 1 over s plus mu when it's multiplied by e to the negative beta s. And so we'll just take this up here. It'll be e to the negative mu t. Anytime we see a t, we'll replace it with a t minus beta. So these four inverse Laplace transforms essentially these are all we need. So now we can go through and finish this. So VO of t. And I don't have room above, so I'm going to put it below. So VO of t is equal to, we'll pull out the coefficient by itself. Finally, I'll get rid of all these extra terms. So it'll be negative alpha RF. So right, this will cancel out this. This will cancel out the squared. So we should just be left with negative alpha over R1. Oh, there's still one of the RFs left. Okay. Now, let's address that term that's highlighted. So what's the inverse Laplace transform of 1 over s? ut. So what we have is u of t. Next, this one. We'll use this down here. So that will give us minus e to the negative 1 over RF CF t times u of t. So now we've gotten rid of that whole piece. Next, plus dot dot dot, but it's actually a minus. So minus, now we got to address this one, which is this times this, right? For that one, we'll use the third row that we came up with, which is going to be u of t minus beta. And then we have the final row, or the final element, which uses this one. So that will give us minus, and actually, I'm going to write it using this form. This will be so much easier. exp just means e to the. So negative 1 over r f cf t minus beta u of t minus beta. And let me use that same form up here. exp negative 1 over r f cf t u of t. So that's it. It's a long road, and I know that you're thinking, can a computer do this, right? So, as an engineer, it's really important to have a good mathematical background, and there's not too many pieces. A lot of EC curricula, ours included, have dropped out some of this stuff. There used to be a lot more of this type of stuff. But a couple pieces are still hanging around. I think it's important to understand it. So I know that this will take some time to digest. I'm hoping you should have a good background on it from ENG272. But this is something you will need to devote a little bit of time to. Okay, yes?
I'm still confused on the final solution. You have this, but at the very beginning, the question was, what exactly is this actually?
Actually, I'm going to show you in a second. I'm going to graph it, and I'll show it to you. Yeah. Okay, so now switching back over to the slides. So another version of it, you can see how it's done. We end up with the same answer right here. So what is this? Okay, we take our op amp, okay? It's a component, or we can call it a process, right? It has a given frequency response. We take our pulse, okay, which is 1 millisecond length and a height of 1, or in this case, we define them generally. So a height of alpha and a width of beta. Okay? We take that pulse, we input it into the integrator op amp, and we get an output that looks like this. What we got when we didn't have the parallel resistor was something that looked like this. It simply ramped down and it leveled off. The version that we just spent pretty close to an hour and 15 minutes working on was trying to get this same solution, but now with the parallel resistor. What we should expect to see is some leakage. Okay, first things first, now this will no longer stay constant because there is a path for the capacitor to discharge, and it will also apply some nonlinearity to the charging. So all I did was I took the function we came up with, which is here in the green, and I made a MATLAB script out of it. So from time equals 0 to 10 milliseconds, with a time step of, I guess, 10 microseconds, calculate our output, which is all this shown right here. I just put in what we had. And the answer looks like this. So you can see, first things first, it doesn't reach all the way down to the negative 10 as it did for the other solution, right? It only reaches about negative 9.6, and then now it doesn't keep the charge indefinitely. It discharges at a rate that's That's shown there.